Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we're going to discuss about your stability theory. So these are the outlines. We're going to start up with the introduction. Then we will going to describe the basic definition of stability. What do you mean by that? What is the BIBO criteria, that is your bounded input and bounded output. Then we're going to discuss some of the stability concept, which will be followed by the stability region in the S-plane, that is where should pole lie in your S-plane so that our system be stable or unstable. Then we're going to discuss the classification of stability, that is your absolute stability and relative stability. And finally we're going to conclude via discussing classification of methods of stability analysis. So stability, it is one of the most important system specification. Obviously, if the system is unstable, in that particular case, your transient response and steady state errors are insignificant points just because system is completely unstable. That is, we cannot predict the outcome of the system. So an unstable system cannot be designed for a specific transient response as steady state error requirements. So although we have already studied about the stability of LTI systems in our earlier courses such as your signals and systems, as far as control systems are concerned, we can extend the basic meaning of stability. So what is stability? In simpler word, we could say that stability of system, we mean that when we apply a variety of input signals to our system, obviously we can apply different sorts of input to our system, and we need to measure the response, or we have to analyze the behavior of the system, how our system will going to behave while applying variable inputs to that particular system. So the system should not produce any unbounded output, but it should produce some valid predictable output. So obviously system designing, the major aspect of your system designing is that we need to obtain some desirable output. And suppose if we are applying some input signal to our system and it is not at all producing any desirable outcome, then the designing of that system will be of no use. So the basic definition of stability of linear time invariant systems could be given as on the basis of applied input and the system output. So a LTI system is said to be stable if it follows the bounded input bounded output criteria, which states that if we're going to apply a bounded or finite input signal, our system should produce a finite or bounded output. And second important point is the zero input should always produce a zero output. If these two conditions are true, then we could say that our system under consideration is your stable system. So while discussing the time domain analysis of the control system, we have learned that we can control the output of the system if the steady state response consists of only the force response. So what do we mean by this force response? But the total response of the system, CT, can be evaluated as it is the combination of your forced response as well as your natural response. So this CT, your complete response of the system, basically consists of two parts, that is your C forced, or you could say the response of the system corresponding to the applied input, and the response of the system when we haven't applied any input signal, or you could say its natural response. So natural response, we could also say that your source free response, that is when we haven't applied any input signal, it is due to the initial conditions only. So forced response is due to the external excitation, that is it is analogous to the outcome or response of the system when we have applied certain input to our system. So using this concept, we can summarize the definition of linear time invariant systems. So using this natural response, here we are considering that we haven't applied any sort of input to our system and we are evaluating its natural response. So a system is said to be stable if the natural response approaches to zero as time approaches to infinity. That is, if we are observing our system at sufficient larger amount of time and when we haven't applied any input signal, and if its response tending towards zero, or you could say that it is converging, then we will going to say that this system is stable. A system is unstable if the natural response approaches infinity as the time approaches infinity. So at sufficiently large amount of time, our response is not bounded and we are getting some unbounded output, or you could say that your output is approaching towards your infinity. A system is marginally stable, that is if the natural response neither decays nor grows, but it remains constant or oscillate. So this is the special case of your marginally stable system. So this is being considered as your marginally stable, where we are getting some finite outcome, but it is of either it is of constant type or it is of your oscillating type of outcome. So in the time domain analysis of the control system, we have also learned that the position of poles may affect the system stability. So how the positioning of pole will going to affect the system stability, or how we will going to comment over the stability of any given system while finding out the positioning of the poles. So let us take a quick review of the concepts and consider the position of the poles at various places. So first case, we are going to consider that we are considering pole at the negative real axis. So what will going to happen, then we will be having this sort of situation where the system pole will going to lie on the negative real axis. So if we consider the simple pole at s is equal to minus a, then the impulse response of the system would have been given as it is your inverse Laplace transform of the transfer function of the system, that will be equal to L inverse of 1 over s plus a, since we are considering pole at s is equal to minus a. So while taking the inverse Laplace transform of this transfer function, we obtain is e to the power minus at. Here this minus sign is indicating that as t is tending towards infinity, this complete e to the power minus a t is convergent, or it is tending towards your 0. Let us understand it with some graph. So simple pole on negative real axis. So let us say that we'll be having this pole at s is equal to minus a. Here this is representing your pole. Then how we will going to obtain its response? So the response Ct would have been given as this decaying signal e to the power minus at. In our last slide we had already seen that. So as t tending towards infinity, or if t is keep going on increasing, then e to the power minus at is a decreasing function like this. So as the time increases, the response approaches to 0 and hence the system is stable. This is what we mean by our Bibo criteria. That is, we have applied some finite input and we are getting this finite outcome, or we could say that at sufficiently larger amount of time we'll be having outcome which is approaching towards your 0. So now let us consider another case. Here we are assuming that pole is lying at the positive real axis. Then if this is the case, then what will going to happen? So if we consider the simple pole at s is equal to plus a, then the simple response of the system would have been given as, again we have to take the inverse Laplace transform of the transfer function, that will be equal to L inverse of 1 over s minus a. Here this s minus a is basically representing that we are considering a simple pole which is lying at s is equal to plus a. So if we're going to take the inverse Laplace transform of this gs, we'll be having this e to the power at, which clearly explains that if time approaches to infinity, this complete e to the power at is also approaching towards your infinity. So now let us again visualize it through some graph. So simple pole, we are assuming that it is lying on the positive real axis. So this is your positive real axis, and let us say that our pole is lying at this positioning at plus a. So how the response of this particular pole will going to be given as we had already evaluated the inverse Laplace transform of this system. The inverse Laplace transform would have been evaluated as e to the power at. As t is keep increasing on or keep going on increasing, then in that particular case our response is also increasing exponentially. So as t is sufficiently large, your response tending towards your infinity. So which is the criteria of your unbounded system. So now we're going to consider our third case, that is pole at the origin. So what will going to happen when the system pole will going to lie at the origin? So if we consider a simple pole at the origin, then the impulse response of the system would have been given as, again the inverse Laplace transform of your transfer function, that will be equal to L inverse of 1 over s. Since pole is lying at your origin, or you could say here in this particular case a will be equal to 0. So while taking the inverse Laplace transform of 1 upon s, what we have obtained is, that is your 1. So the inverse Laplace transform when pole lies at the origin, that turns out to be unity. If multiple poles are on the origin, then what will going to happen? Obviously, in this particular case, we'll assuming that double pole at the origin. So since we are assuming double pole at the origin, so that is why the transfer function would have been written as 1 over s square. If there are triple poles, if there are 4 poles, or if there are 5 number of poles, then similarly the power of s will going to increase as per the number of poles. So here in this particular case, we are assuming that there are 2 number of poles that are lying on the origin. So when we're going to take the inverse Laplace transform of this 1 over s square, we are left with this t. Now let us again understand it through some graphical analysis. When we're going to assume that single pole at the origin, so this is the case where single pole is lying at the origin, then what will going to happen to our response is, our response will be a constant one, or you could say your unit step signal in this particular case. And when we're going to have double pole at the origin, so one pole has already been mentioned over here, and when we're going to have 2 poles at the origin, then what will happen to our response is a straight line or constantly increasing function. So now let us take another case where the complex pole in the left side of the S-plane is lying. So let us consider that the transfer function has the complex conjugate poles at S is equal to minus alpha plus minus j omega. So the time response would have been given as gt is equal to inverse Laplace transform of g of s. So that will be equal to L inverse of 1 over s plus alpha minus j omega plus 1 over s plus alpha plus j omega. And when we're going to take the inverse Laplace transform of this gs, what we're going to obtain is that will be equal to 2 into e to the power minus alpha t cos of omega t. So if you closely observe that here, this negative sign is basically saying that, or it gives us the information that as t tending towards infinity, our whole response of the system, which will the multiplication of this cos of omega t, this is your oscillating signal, and e to the power minus alpha t, as we had already seen that e to the power minus at is a exponential decaying signal. So when this exponential decaying signal is going to get multiplied with this one, then we will going to finally have convergent response or zero signal as t tending towards your infinity. So now let us understand it with some graph. So complex pole in the left side of the S plane. So suppose that this are the complex pole, that is minus alpha plus j omega and minus alpha minus j omega. So if these are the positioning of poles, then how it will going to affect our response is, then the response can be given as by this particular figure. So if we closely observe that, we have evaluated the response as 2 into e to the power minus alpha t cos of omega ct. So this oscillation is due to your cos of omega t, and this envelope is basically showing the decaying exponential signal. So as we had already said that if t is sufficiently large, then our response of the system is tending towards your zero, or it is your convergent response. So now let us take another case where the complex pole is going to lie on the right side of the S plane. Then what will going to happen? So let the transfer function has the complex conjugate poles at S is equal to alpha plus minus j omega. Then in this particular case, the time response can be given as, again, the inverse Laplace transform of your transfer function, that will be L inverse of 1 over s minus alpha minus j omega plus 1 over s minus alpha plus j omega. So the inverse Laplace transform can be evaluated as 2 into e to the power alpha t cos of omega t. So this is clearly indicating that as t tending towards infinity, this complete response is also tending towards your infinity. So let us understand it with some graph. When the complex pole in the right side of the S plane, so the positioning of poles are demarcated by this particular pole sign or cross sign. So one pole is at your plus alpha plus j omega, and another pole is your plus alpha minus j omega. So if this is the situation of the poles, then how we will going to obtain the response, or how our response will going to look like? So it will be look like this one, e to the power at, this is your constantly increasing exponential function, and this oscillatory sort of, or this sinusoidal sort of signal, it is due to the factor of your cos omega t. So we can clearly observe that as t tending towards your infinity, our response is also tending towards your infinity. So now let us take the another case where pole lie on the j omega axis. So if a pole is lie on your j omega axis, then what will going to happen? So if we consider a complex pole lie on the j omega, then the time response of the system can be given as again the inverse Laplace transform of your transfer function g of s, that will be equal to 1 over s minus j omega plus 1 over s plus j omega. So that turns out to be 2 times of cos of omega ct. So cos of omega ct is your oscillating signal. So you could observe that the response of our system is your oscillatory just because of this cos of omega ct. It will neither decays nor grows. So now let us understand it with some graph also. So what will going to happen when pole is lie on the j omega axis? So let us say the poles are lying on this j omega axis. These are basically showing the positionings of poles. So how our response will going to look like in this particular scenario or in this particular case? So the response will going to look like this one. Cos of omega ct, this oscillation is due to that particular thing only, and this is basically representing the peak amplitude of that particular thing. So in our last slide we have already seen that this peak amplitude will be equal to +2 and -2. So this particular response is not at all increasing, or you could say nor growing nor decays, although it is your constantly oscillatory. So let us quickly review what we have learned so far. So the closed loop system poles that lies in the left half of the S-plane yields either pure exponential decay or damped sinusoidal natural responses. This is what we have understood it with the help of graphs, as well as we have already evaluated via finding out the inverse Laplace transform of the transfer function. So poles in the right half plane or yields either pure exponentially increasing or exponentially increasing sinusoidal natural responses. So we can conclude that the position of the closed loop poles plays an important role in the characterization of the system stability. And how we can comment on that particular system stability, that is via observing the system response. That is, if it is your bounded one, obviously we have to evaluate the stability of the system with the help of that Bibo criteria. That is, if we are getting some finite response, then we are going to characterize them as your stable, and if we are getting this unbounded outcome, then we are going to characterize them as your unstable system. So we could extend this learning with the stability of the system as it is related with the natural responses. So hence, with the same reasoning, we can also determine the stability of the system based on the system poles. So obviously, if we have got the transfer function of any system, then while obtaining the positioning of the poles, that is where they are going to actually lie in your S-plane, we can specifically comment on the stability of that particular system. So stable systems have closed loop transfer functions with poles only in the left half plane. So if the poles positioned at the left half of the S-plane only, or then we can call them as your stable system. And unstable systems have the closed loop transfer function with at least one pole in the right half of the plane and or poles of multiplicity greater than 1 on the imaginary axis. So if the poles are lying on the right side of the S-plane, even if it is single pole only, then also it will going to make our system unstable. So when we're going to say that our system is marginally stable? So marginally stable system have closed loop transfer function with only imaginary axis poles of multiplicity 1 and poles in the left half plane. So all the poles must have to be lie on the left half of the S-plane, or you could say that it is lying on the j omega axis, then only we can say that our system is marginally stable. So let us understand it with some closed loop system example. So let us say this is our given system, that is the open loop transfer function is given to us, that is your 3 upon s times of s plus 1 into s plus 2. So here applied input is your 1 over s, and cs is the response and es is the error signal, which is the difference of your cs response and your applied input. That is, here es will be equal to rs minus of cs. So this is the closed loop system that is given to us, and we have to find out whether this particular system is stable or unstable. So let us plot the poles in your S-plane. So stable systems closed loop poles will going to lie on these places. That is, one is lying on your negative j omega axis, and these two poles are lying on 0.164 plus j omega, and this one is your 0.164 minus j omega. You can easily evaluate your closed loop poles such as for that particular thing we need to evaluate the closed loop transfer function, which is nothing but gs over 1 plus gs times of h of s. So when we're going to solve the polynomial equation of this third order, then we're going to obtain three poles. So their positioning will going to looks like this. So we can easily observe that all the poles are lying on the left half of the S plane. So we can comment on the system stability that this particular given system will be your stable one. So this particular figure is basically showing the response of the system, and this is basically oscillatory response is this oscillatory response is basically showing the response of this particular system. So we can observe that the system response is approaching towards 0 as t increases, or we could say that your response is the convergent one. So this is the closed loop poles and response of the stable system. So now let us consider another example. So here in this second example, we'll be having this open loop transfer function would have been given as 7 upon s, s plus 1, s plus 2. And the input signal applied r of s, obviously in your Laplace domain, that is equal to 1 over s, and cs is the response of the system. So in order to find out the positioning of poles of the closed loop transfer function, first of all we need to evaluate the closed loop transfer function, which is equal to gs over 1 plus gs times of hs. So when we're going to evaluate that polynomial equation and solve them for the values of s, then we will going to obtain the different values of poles or different positions of poles. So these are the positioning of poles. This one is lying on your negative real axis, and these are your two complex pole which lie on the right side of the S plane. So since two of the poles are lying on the right side of the S plane, so this system is your unstable system. So the outcome of this particular system can be given as like this one. You can easily get the idea that the outcome of this particular system is oscillatory as well as increasing. That is, in this particular case, our system outcome is your unbounded one, or we could say that as t tending towards your infinity, our system response is also tending towards your infinity. So this is basically showing the closed loop poles and response for the unstable system. So now let us discuss about the stability region in your S plane. So this particular dark purple color region is basically showing your unstable region, or we could say that this is your right side of the S plane. So if any pole is lying in this particular darker portion of the region, in that particular case we're going to consider our system, or we're going to say that our system is unstable system. And if poles, obviously I'm talking about even if suppose if a particular system is having 10 number of poles, and if only one pole is lying on the right side of the S-plane and all 9 poles are lying on the left side of the S-plane, then also we're going to demarcate our system as your unstable system. That is, if any of the pole is lying on your positive side of the S-plane, so it will going to make our system unstable only. Whereas if all the poles of the system are lying on your left side of the S-plane, then in that particular case we're going to classify our system as your stable system. And this is the special case if poles lie on your j omega axis and some poles lie on the left side of the S-plane, then we're going to say that our system is your marginally stable system. So now we're going to discuss the classification of stability. So mainly stability can be studied in two parts. Number one is your absolute stability and second one is your relative stability. So this absolute stability will going to gives us the answer in terms of binary. That is whether a given particular system is stable one or unstable one. Whereas this relative stability will going to gives us the information about the system, that is our system is stable or unstable with respect to any other system, or you could say that if system is your stable system, then how much stabler it is than your other system. So absolute stability signifies whether a particular system is stable or not. So it is simply giving us idea whether a given system is your stable or unstable one. Whereas the relative stability gives us the information about a particular system, that how much stable a system is actually gives the degree of stability in contrast with your other system or any given system. So now we're going to discuss the classification methods of stability analysis. So we'll be having two types of systems, that is your absolute stability and your relative stability. So in our absolute stability analysis, is based on the coefficients of roots of the polynomial, and we have to characterize our system whether it is absolute stable or not. We'll be having this criteria, that is your Raoult-Hurwitz criteria. Whereas in relative stability, this relative stability analysis based on the frequency domain graphical representation of the system transfer function, and what are the different mechanisms by which we will going to find out the relative stability of our system, that is your root locus, polar plot, Bode plot, and Nyquist plot, that we have to study in our upcoming lectures. So hopefully you guys have got the basic insight of the stability, that is how depending upon the positioning of poles we are in a state to comment over the stability of the system. In case of any doubt, you can ask me in the comment section. I'll try to solve them out as soon as possible. So these are the references. Thank you very much for your patient hearing.